Ladies and gentlemen, I'm going to start with my thanks to Jerry Pollock for allowing me to present this paper by this technology. And unfortunately, hospital schedules are not too flexible, so I had to do this. I'm going to present my view of the structure of water, starting in my tradition in materials science. I started my career, as it happens, on water sols, at the beginning of the solution sol gel process, which is now perhaps the most referred to paper in all of material science. But most of my work has been in very hard materials, all the way down from diamonds to all the gems and so on, and including alumina, which is of course very important for all of us. But I have been, in the last 5 years again, connected to water as a condensed phase. So I'm going to bring to you my broad experience across that spectrum of different classes of materials. And I'm going to start by showing you that the changes which I know exist in water are hardly unreasonable for a material scientist. So it's hard science on hard materials where I start. Unbelievable changes have been discovered in condensed matter, that means solids and liquids, with electromagnetic radiation. Totally unbelievable. I show you the website to which you can go to get about 20 papers perhaps, and a large number of course now in Japan, on the role of electrical and magnetic fields in changing crystalline solids. All the most important solid materials in modern technology, silicon, the ferrites, the insulators, titanates, all those, in a few seconds, exposure to a microwave field can have their structures totally destroyed. So why is it what can happen with water, of course? Now, I happen to have taught thermodynamics for about 40 years at Penn State and Arizona State, and in all the phase rule texts, they only say that there are two intensive variables, pressure and temperature, which can affect G, the Gibbs free energy, and therefore that's all we need to look at. So our whole community of material scientists is very biased towards only thinking about those two intensive variables. But of course, electric and magnetic fields are obviously candidates. Well, we usually say, these are all de minimis, forget them, they're too small anyway. And the question I'm going to raise with you and show you, can E and H fields change G enough to cause phase transformations? Okay, absorption of energy from microwave fields is absolutely non-uniform. In the microwave racket in our business, microwave matter reactions, they always think it's electric field which is the cause of the heating. That's how we heat materials, how you heat your water and your food in your microwave oven and so on, and it's the dielectric loss only. Wrong. That is simply wrong. The complete equation must include the magnetic field. They put it up there too, and so you must see that you really must have that magnetic component. But our experimental data started to clash with all this ignoring of E and H fields. The effects are dramatic. And furthermore, so when we take this to the theorists, they say this can't be, this is weird. We don't do magnetic fields in physics. Okay, that's nice. And then when I throw at them the fact that not only is it the magnetic field, but we are seeing huge differences between AC fields and DC fields. Well, they say, what are you doing to us? So the theorists are really not very helpful at this point. So I'm going to give you the experimental data. I'm an experimentalist. I'm in the Faraday tradition. I just do the experiments, simple experiments. Forget about the theory. Okay, fantastic is the only word that everybody says when they look at the data. If they look at the data that we have amassed, the proper term is fantastics. Okay, completely different phases are formed. we completely transform crystalline matter into amorphous, non-crystalline solids in seconds. The Japanese call them nanoglasses, without melting. What are we doing? In some way, we know we are coupling to electron spins because empirically, I've run 100 substances. That is an essential component of. Experimentally, it's very simple. There's a TE103, transverse electric 103 cavity, in which we set up a standing wave for the 2.45 gigahertz field. This is the regular home oven frequency, and you can locate them at the maxima at A or B. And here's the experimental setup. It's one complicated gadget which you can buy for about 10,000 bucks. You can build for 10,000 bucks. And there you can see the locations inside a silica glass tube holder in which we can control the gas. So there we go. I'm going to give you just one example of showing the dramatic effects. This is the X-ray diffraction patterns of the starting materials, that's barium carbonate and iron oxide. And you see the X-ray diffraction pattern, and you notice that after 90 seconds we've got a well crystallized barium ferrite at the top. It normally takes about 10 hours if you do it in a conventional furnace. Now I want to show you the difference. This is in the magnetic field. The last slide was the electric field maximum. This is 3 centimeters away. That's the only difference. And you notice that in 5 seconds, please, if you're a material scientist, you should grasp it. 5 seconds. It normally would take 10 hours to move the atoms in the material. In 5 seconds, we have homogenized everything. In 5 seconds, I keep repeating that, it is so extraordinary. And you notice it's completely amorphous. I mean, this is a Bernal heap packing if there ever was one. And you notice after 90 seconds, still completely amorphous. Now that's the difference. First, the fact of the difference between E and H. Second, the fact that we're making crystalline matter go to totally new glassy forms. Now here I'm just illustrating the difference. Here's titanium oxide, the principal insulator of today's world, and here it is slightly reduced, and in 30 seconds it's gone to amorphous, completely be gone. And this shows you we've used all the techniques, DEM, everything else, and here's Raman showing how the titanium goes. Now, what's my conclusion? If crystalline solids with 4+ ions, that means the strongest bonds, think about that, can be so dramatically changed, so can water. So beginning of my lack of skepticism is that. So we said, can we change water? And here's the sodium chloride solution, and we did the crystal growth of sodium chloride. It's a long study which will be presented in a month at the Materials Research Society. On the left you see there's a septum in between. On the left is with no illumination, you get barely any nuclei forming. On the right hand side, exactly the same conditions but illuminated with sodium D line. That's 589. Now look at the funny thing. These, I'm skipping a lot of stuff which will be in the paper, is we are growing millimeter size crystals. These are very perfect actually, they're centimeters when they're grown, from thermally unsaturated solutions. So that we are doing it where there's a 3% deficiency of concentration of sodium ions, and yet we are growing crystals. So what am I doing? When I saw that, I said we are changing the thermodynamics. The saturation of NaCl in illuminated water is lower than in regular water without. So now we come to, let's go from those photons, say about 1 eV, 1 or 2, 3 eV, down to 2.45 gigahertz microwaves. You'll see what happens. Here are the gadgets made by Dr. Sedelmaier in Phoenix, and he's got a device in which he boils water in a vectored field. I show you what that means. This is from his papers and patents. You notice that a little antenna from your $5 microwave magnetron is sticking up in the water, and the H field is in the plane and the E field is perpendicular, and so he boils water in this funny condition. I forget everything else. Can it change the structure of water? Well, he boils it once, twice, you see, all the way down, and you see that in a way the structure of the water by UV vis and by Raman is certainly changing. And the funny thing is that the Raman spectrum, the main stretch frequencies of OH are dropped that much. So it has an effect on this, and these large. Now this is checking with decay time and so on. So we can see basically that we can take ultra pure water and hit it with a microwave vectored field, and we can get it to change its structure, and it survives at least in the order of hours. Then we come to the second most interesting, that was brought to us in April of this year, and in August of this year I was looking at somebody sent me a attachment, a YouTube attachment, and I said, what the heck is going on? A man called Mr. Kanzius discovered in Erie, Pennsylvania, that he could, quote, burn salt water. That is what he made no claims whatsoever about the energy balance and all that stuff. So this is a polarized 13.56 megahertz beam. That's all. You can see that's in our lab, our work done on at least 100 samples, different solutions, etc., etc., and we're hitting that water solution or pure water with that beam, and we are igniting the products of water, which have been dissociated, electrolyzed without electrolysis, without electrodes. So what Faraday did in 1831 has been updated. You don't need to have the you don't need the electrodes, and you don't need to pass any current. So it is in fact roughly the net condition is that salt water is being burned to yield water. Not a bad, it's a tree hugger's dream, as I say. Forget the energy balance, we'll know it in a couple of years. It took us 20 years to figure out corn to ethanol, so let's not be in a hurry on. Okay, there's some little data for you, just that's the experimental setup, and there are no plasmas involved. People are saying what's happening to the energy, etc. At least in that wavelength range. We're not being able to see the hydrogen lines and so on, but it's a clean sodium line only, which is adventitious introduction of little droplets into the water. But the sodium concentration increases as the water. And then we looked at the structure of these, and again you see the same kind of thing. You notice first the black line, sodium chloride before, pretty much the standard one, water solution, and the stretch bands are right. It goes down as it does with the Sedelmaier stuff in microwaves, and then we measured it after 2 hours, it had come back some. Then we measured it after 6 hours, 6 days, and it had relaxed all the way back. Very comforting to see that there was not, is really. Now, a second family of experiments which I have done to see if water can be structured in other ways. So we have established that microwaves and radio waves can structure water. I turned then to another example. Why? Because it had biological implications. We had found that a whole range of silver aquasols, I'm using the terms precisely, metallic silver aquasols actually had very important biological properties. So we did a thorough characterization as material scientists would do, and with tools. And this is just to start you off an extraordinary biological activity of these ultra dilute salts. 1 ppm of metallic silver balls in water, ultra pure water, ultra dilute, ultra pure, and it is as good a antibiotic or antibacterial as it does most of the bacteria and a few viruses, and in fact it does very well on malaria now and even on MRSA. So that was impressive enough for us. How is it doing it? So we looked at this is the actual sample that was supplied by one manufacturer. I claim nothing that this is the only one that does it. I imagine that most pure aquasols will do exactly the same thing. And we checked them. We checked their chemistry, we checked their structure, and typically they're 30 nanometer clusters, and these are really aggregates which we can see in the cryo-TEM, how they boil off and they leave a structure of about 6 nanometer particles, which actually disintegrate and fly off. And you can see by the HRTM, they're really metallic silver. There's a little bit of oxide layer sometimes, and so on. Now, let me suggest one interesting bridge now to the radiation work. This is a name you will remember. Juliana Brooks used to be a professor at Ohio State, has moved to a company called General Resonance in Baltimore, and she did the experiment of just shining a heated silver filament over the same petri dish. It has the same effects. So, equivalence now of the colloid with a radiation. And we looked at the same thing with, are these structures different? And this is done not with the same instrument, therefore you see the lack of resolution at 3445 peaks, because this is a different geometry. That is an immersion laser, and this is done from outside. So, but by and large, again, a changed Raman spectrum for the silver balls. Now, two other lines of evidence. This is Samal and Geckeler's paper about 5-6 years ago, where they essentially showed that distribution of a solute was totally irregular in a water solution, and that they got this clustering that very dilute small areas seem to form where the concentration is high as compared to the rest. In homogeneity in dilute solutions. This is our chairman's work. I'm sure he'll have shown you this, and you can see it's right up to date. And what it's telling me is there's no more to be said. You can get segregation of structural units in the, even to the pH segregation, of course, in water with 2 electrodes in it. So we are now used to the fact that from many lines of evidence we have the fact that water is easily structured. Summary. Facts are voluminous, indisputable, compelling. Radiation can and does drastically change solids and liquids. Work by many authors, some in this audience, have also shown the same thing, of course. Some of these lines are a little more spectacular. Okay, fantastic is the only word that everybody says when they look at the data. If they look at the data that we have amassed, the proper term is fantastics. Okay, completely different phases are formed. I am going to go through very rapidly because a lot of this stuff is published. The two papers, both in Materials Research Innovations, one in 2005 and one in 2007. And the first is a very long paper on structure. Most of what I'll be saying is summarized there, so I will just go very quickly through it. How do we determine structure? For crystalline solids which are homogeneous in structure, what do I mean by that? They're periodic from nanometers to infinity. So the data are ultra precise, thousands of a nanometer, thousands of an angstrom even. Diffraction works to give us structure very precisely for solids. For liquids and gases, they are very fuzzy. We lose periodicity, the boundary condition for diffraction. But we learn enough from diffraction and scattering of X-rays as well as light rays that they are nano-heterogeneous. Heterogeneous on the nanometer scale. That is absolute, the description of all. Just to illustrate, here is a garnet, a structure which I worked on years ago, and there are 3 intertwined polyhedra. I'm showing you only the 2 of them, the tetrahedra and the octahedra, and those little green dots are the exact positions of the average positions where the center of gravity of each of those ions lies. And you know them. And if I add the 3rd polyhedron, which is a cube, 8 coordination, you can see where they fit in. So there are no molecules here, but they're artificial arrangements which we can put into, for the graduate students, into polyhedra. But those are ultra repeatable, exactly the same, perpetrated for 10 meters. Now let's come down to the fuzz line between crystalline and glassy or liquid matter. Here's a thing from my friends in Japan, three-phase perovskite structure or something, meeting at a little area where they meet, the composition and the structure, it all becomes fuzzy, as you can see. So crystalline matter becomes amorphous matter in that region, say at a little triple point where they meet, and we've blown that up. You can see the 1 nanometer scale, and what do I show you? That all the crystallinity, the ordered structure is gone, but more than that, that you can see a little bit of sub-nanometer and nanometer size regions of different composition, hence the background scattering, the absorption is different, and of the lack of periodicity. Now, water itself, in its condensed phases, what about its structure? What do we know about it? First, water does exist in at least 10 crystalline and several non-crystalline structures. So there's no ifs, ands or buts about it. It's normal. What water can be quenched to a glass? Just by dropping into liquid nitrogen, not a big deal. And I should say, for those who muddle this up with the femtosecond relaxation times of bonds, there's nothing to do with that. These are phases which stand side by side for days and weeks and years and blah 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 and so on, under the right PT conditions. Relaxation times of different changes by electromagnetic, acoustic and so-called chi fields all appear to be in hours. So we know that these are nothing that's going to disappear in a femtosecond. And this has a little, I don't know why I'm no champion of homeopathy, but the fact is that the changes to structure are important, not the composition, like pressure, temperature and epitaxy and so on. Hence the poor argument, unscientific argument used against homeopathy is null and void, that if it doesn't have any compositional change, it can't be different. No, we have 50 different structures of water, radically different. So it's a very bad. Now, back to what is the structure of a liquid. Unfortunately, Professor Zakariasen at Chicago and came from Oslo published this image of random network structures, as he called them, which are covalent structures, which are liquid, which could be applied to liquid. These were for glasses, which is a frozen liquid. And this has stuck for 60 years in the minds of graduate students, unfortunately, because they're lazy. The thing that happened on the way to the forum is some Russians did, instead of X-ray diffraction, which is a very poor tool for trying to get structure from non-periodic lattices, they just took TEM. They're looking at the structure. And what Paraykoshyts, the director of the institute in Leningrad, showed was incontrovertible proof that every transparent looking glass is heterogeneous to beat the band. You look at the different phases. No, these are pretty big things. They are kind of nanometer stuff, tens of nanometers. And you look inside there, even at the bottom diagram, you see that two blobs have come out of different shapes and sizes, and B, that each of those two blobs have then phase separated within them. And this results from a paper I wrote in 1960, of which I'm very proud. It was just a 2-page paper in which I said any non-ideality in solutions is a hint that you can phase separate. Now, as you know, very few things are ideal. So very few liquid solutions are ideal. So this is a hint that you can get phase separation. And Paraykoshyts mentions that in this paper in 84. That is a seminal paper saying why the thermodynamics, why is it what can happen with water, of course. Now, I happen to have taught thermodynamics for about 40 years at Penn State and Arizona State. And in all the phase rule texts, they only say that there are two intensive variables, pressure and temperature, which can affect G, the Gibbs free energy, and therefore that's all we need to look at. So our whole community of material scientists is very biased towards only thinking about those two intensive variables. But of course, electric and magnetic fields are obviously candidates. Well, we usually say, these are all de minimis, forget them, they're too small anyway. And the question I'm going to raise with you and show you, can E and H fields change G enough to cause phase transformations? Well, 2004 I gave this paper in March in Washington, and in April or June there comes the um, phase diagram of water from Kawamoto in Japan, in which he again finds a phase boundary between what he calls sparse water and dense water. Of course, unknown to him, there must be from each of those triple points another line coming out. So we are saying that water does, experimentally, and in the liquid stable region, leave alone the metastable possibilities, have different structures which are stable. Now let me suggest one interesting bridge now to the radiation work. This is a name you will remember. Juliana Brooks used to be a professor at Ohio State, has moved to a company called General Resonance in Baltimore. How does this all relate to Martin Chaplin's masterful compendium of molecules and oligomers? There is no conflict whatsoever. Martin Chaplin's compendium gives us all the molecular building blocks, the possible and probable building blocks. That is the molecular level of structure. We at the material science level, we talk about the structure of a condensed phase as the architecture of the house. In this building, you've got, I'm sure there are bricks and wood and all kinds of cement blocks. Those are the molecular building blocks. But the structure consists of bathrooms and conference rooms and huge entry areas and so on. That is the structure of a condensed phase. It's the architecture, not the building blocks. And that's the relationship between. I am going to go through very rapidly because a lot of this stuff is published. The two papers, both in Materials Research Innovation. Here are some big ones. I don't know, I think that last one is about 280 water molecules in it. So in the condensed phase, we must say, how do we put these together? How many of these are there in this particular temperature and pressure or whatever we... And the first law of material science says that properties are determined largely by structure. They're continuously changed by solutions and all that, but it is structure that counts. So composition is not as determinative. You want an example? The demo. Graphite and diamond. The softest material in the world, the hardest material in the world. Identical compositions. Enough said. So this is from D. Benedetti and Stanley's wonderful review of the structure of water in Physics Today, and you can see when you get properties changing like that, all near room temperature, mark you, you know that there must be huge. I've done a lot of work on thermal expansion in the right hand figure, and you can see that negative thermal expansion switching to a low flat thermal expansion with temperature in the space of about 20 degrees. Well, you know a lot that the properties have changed, hence the structure has changed. End of discussion. So we know that many structures in liquid water have just been misidentified and not forgotten. How does this all relate to Martin Chaplin's masterful compendium of molecules and oligomers? There is no conflict whatsoever. Martin Chaplin's compendium gives us all the molecular building blocks, the possible and probable building blocks. That is the molecular level of structure. We at the material science level, we talk about the structure of a condensed phase as the architecture of the house. In this building, you've got, I'm sure there are bricks and wood and all kinds of dense matter. Here's Bockrus and Reddy, the electrochemist's view, and it's pretty well identical, bigger and smaller and different shapes and sizes. Now, the second family of experiments which I have done to see if water can be structured in other ways. So we have established that microwaves and radio waves can structure water. I turn then to another example. Key conclusions. Liquid water is a condensed phase according to the absolute thermodynamic considerations above. It is required that it may assume many different structures. Empirically, the data now prove that it does. In addition, I want to end on this. There are two other ways of causing even other new metastable structures. One is epitaxy, and the other is the presence of. Ladies and gentlemen, I'm going to start with my thanks to Jerry Pollock for allowing me to present this paper by this technology. And unfortunately, hospital schedules are not too flexible, so I had to do this. The next way to do it is nanobubbles. When you shake up water or anything like that, you can trap nanobubbles, and how they're distributed and what effect they'll have on the structure. This may be related to Samal and Geckler's work, etc. That Tyrrell and Attard's paper from Australia actually took some pictures of them. So yes, they're real and they affect. And these two have some relevance to the homeopathy debate, in which I know nothing more about homeopathy than that. What about explanations and theories to explain all this stuff? As usual, these will lag the facts by many years or decades. Nobody has come close to explaining our microwave effects on crystalline matter. Continuous radiation on salt water will take 10 years at least. What happens there? So, radiation effects, there are lots, many in the audience here, but I do refer you again to the work of Juliana Brooks. If you go to Google and just look up her lengthy patents, they're 50 pages long, between 1999 and 2007, she may give a hint towards where the emergence of new theory will be. It looks like there's a kind of a black hole in physics. If you go back to the 1901 Planck paper, the 1905 Einstein paper, they do set certain boundary conditions, kind of excluding this interesting phenomenon of resonance. The energy balances, if you wish, in the resonance condition. Summary. It is absolutely certain that there exists an enormous array of structures in liquid water, stable and metastable. Second point. It is erroneous to muddle the kinetics of condensed phase changes, stable and metastable molecular dynamics. The commonest solid and liquid changes cover the range from seconds to hours to infinity. Ask De Beers about diamonds. They're forever.